In this video, we're taking a look at solving these Kirchhoff's law problems. So these are circuit problems that have multiple batteries in the circuit, and with the batteries on different branches. And to solve these, you'll need to use Kirchhoff's loop law and Kirchhoff's junction law. So what I've done is I've gone ahead and taken the problems and made them, printed them out a little bit larger on their individual pages like this, make it a little bit easier to talk about. So here's problem 1. And you can see that we have 3 batteries and 3 resistors set up like so. They've gone ahead and arbitrarily labeled directions on the currents here, calling the current here I1, the current here I2, the current here I3. Taking just a quick glance at that, you're like, well, that's crazy. I can't have all 3 currents leaving this junction. There's no way. I mean, where the charge is coming from. So we know that at least one of those currents will be going in the incorrect direction. And that's all right. The point of this is just so that everyone who does this problem all choose the same notation so that we all know which one we're talking about when we're talking about current 1, current 2, current 3. And then we all get the same answer. I'm going to do my junction law. We're going to choose to do the bottom junction where they draw the currents. And so we're going to do the sum of the currents going into the junction equals sum of the currents going out of the junction. There's nothing going into that junction. So it's really just going to be I1 and I2 and I3 balancing out, adding up to 0. Now we're going to go ahead and do some loop laws. And we can choose to do the left loop, the right loop, outside loop. I'm going to choose to use left loop and right loop. So for the left loop, I'm going to choose to start at the low V side of the biggest battery, and then travel around through the battery and around back in a complete loop, so that I start off with a nice positive voltage going from low V side to the high V side for that battery. So I have a nice big constant positive term to start with. So up 12 volts. Now I'm going to have I2 flowing through the 8 ohm resistor. So delta V for resistor is IR. I'm going with the current from before it lost the energy to after it loses the energy, my hypothetical positives flowing through. And so I'm going to go down IR, so down 8 I2. Now I'm going backwards through the battery like this. So I'm going from the high V to the low V side of the battery. So I'm going to go down 3 volts. Now a setup like this will happen when you're recharging a battery. You'll have some higher voltage here that's going to push charges backwards through this. It'll make that little chemical reaction inside the battery between the 2 metals run backwards, and you'll be recharging the battery. So that's why you would have a battery set up like this, for example, one reason. Current's going to flow around. Now it's here. I'm going with I2 through the 6 ohm resistor. So again, I'm going with the current before it loses the energy to after it loses the energy. So I'm going to go down IR. So I'm going to go down 6 I2. That gets me back to my starting point, so that's equal to 0. Now I'm going to do a loop law around the right loop. I'm going to choose to start at the low V side of the biggest battery. Again, you don't have to do it this way. It's just the way I like to always start mine. And I'm going to travel around going through that big battery around in a loop like this. So I'm going to go counterclockwise through this one. So first, I'm going to go through the battery up 6 volts. Now I'm going to go backwards through that battery down 3 volts. Now I'm going to go with the current. So again, with the charge from before they lost the energy to after they lost the energy, we're going to go down IR. So we're going to go minus 10 I1. That gets me back to my starting point. So that's equal to 0. Now I have my 3 equations I'm going to use to simultaneously solve the system of equations to solve for my values for the different variables. One of the first things in this really nice circuit, because I don't have any resistors on this center branch, you'll notice that in my loop laws, I don't have any terms with I3. And I was able to do a loop with only one current involved with resistors, which means I only have one variable in that equation to solve, which will be really quick to solve for I2, really quick to solve for I1 here. I'm going to make life good. So I can rearrange this loop law, and I should be able to solve, get my constant terms together. 12 minus 3 is 9. Move the I2s to the other side. So I'm going to have 9 equals, what is that? 9 is going to equal 14 I2. Rearranging, you get that I2 is 9/14 of an amp. Okay, working with the green one. You say again, I only have one variable here. Rearranging this, 6 minus 3 is 3. So I'm going to end up with 3 equals 10 I1. Rearrange again, you say, I'm going to see that I1 is 3/10 of an amp. Now I can go ahead and take these values and put them into the junction law. And when I do that, that's what I1 plus I2 plus I3 is 0. So it's going to be I1 is 3/10 plus I2, which is 9/14, plus I3, which we don't know anything about, is going to equal 0. Okay, I1 plus I2 plus I3 is 0 using this equation, putting in our values, and say, well, gosh, that means I3 is going to be equal to, now I need to sum these two together, right? They move to the other side, they both be negative. So I got to sum these together, tenths and 14ths. You're like, okay, the lowest common multiple is going to be, well, it's going to be 70ths, but what the heck, let's just go up to 140ths, just make life easy. So times 14 over 14 and times 10 over 10. So it's going to be 42 plus 90. So that's going to be 132 140ths. And I can go ahead and I can reduce that to lower terms. You can say, hey, I can see that, let's see, even numbers, so you just do twos, and you say, hey, that's going to be 66 over 70, which I can reduce again and be 33 over 35. So it's going to be negative 33 35ths amps. So now it might be a good idea to just make sure this makes sense. You notice this one came out to be negative. That means the direction that was assigned for I3 is backwards. So I3 is actually flowing down into this bottom junction. And so what's happening is the current is coming down, and it splits, comes around, comes back in, splits, comes around, rejoins up, comes back through. So the current is actually flowing this way in the circuit. Right? And that makes logical sense. Look, the 12-volt big battery, it's going to be pushing current this way, and the 6-volt's going to be pushing current this way, right? And they're going to kind of overpower and push it backwards through that 3-volt, like as if they were trying to recharge that little 3-volt battery, for example. So that makes sense. The way it comes out, the signs all make sense. Well, problem number 2. This one is kind of interesting to look at the diagram and compare it to the diagram from problem 1. And you say, hey, look, 8 ohm, 3 volts, 12 volts, 6 ohm, 6 volts, 10 ohm. Hey, it's the same circuit. There's only one little change. And that change is, look, they flipped this battery around. All right. So now the big 6 volt is trying to push current that way instead of that way. And so we're kind of anticipating there are going to definitely be changes to the circuit, to the results we get. So we are not anticipating getting these same results out. So doing a junction law, and I'm going to do it for the bottom junction. We're going to say currents in equals currents out. There are no currents going in towards the junction. They're all going out. So I'm just going to go ahead and do all of them going out. I1 and I2 and I3 sum to 0. Okay, now we're going to go ahead and do our loop laws. So we will go ahead and do a loop on the left side. Again, I'm going to start at the low V side of that 12-volt battery, right? And go, right? Okay, and again, I'm going around the circuit. I'm choosing to read the circuit this way. I'm not necessarily saying that I2 is going to go in that way, although it is in this one. But I'm just choosing to read the circuit going clockwise. So first, I'm starting at the low V side of the battery. I'm going to go up 12 volts. Okay, so these are our loop laws. Okay, and I'm doing the left loop here first. So I'm going to go up 12 volts. Then I'm going to go with the current, with I2. I2 is labeled as going this way. So I'm going from before it loses the energy to after it goes through the resistor and loses the energy of those charges. So we're going to go down potential. So we're going to go down 8 I2. And then we're going to go backwards to that battery. We're going to go up, down, down 3 volts. And then we're going to go with the current through the 8 ohm resistor, 6 ohm resistor, I should say. And so we're going to go down 6 I2. And that gets me back to my starting point for my loop reading the circuit. So I should be back to back to the same potential I started at. So the sum of all these rises and drops of voltage, I should end up back where I started, total change being 0. So now what are we doing? What we're doing is we're like adding up all the delta V's is really what we're doing here, right? Looking at the total change. Okay, let's go ahead and do the right circuit. And so the right circuit, should I set it up like I did last time? Okay, last time I started here on the circuit. Normally I would start the low V side and go through that way, but I'm trying to make it look like it did before. So last time we went around counterclockwise through the right circuit. Let's go ahead and do that this time too. Going around that way. So first I'm going to go from the high V to low V side. So when I do that right loop, okay, I'm actually going to go down 6 volts. Okay, now I'm going against the battery. I'm going to go down another 3 volts. You see, this doesn't make sense, right? But yeah, we're going to go down 3 volts. And then I'm going to go with the current through the 10 ohm. If I'm going with the current, I'm going to go from before it loses energy to after it loses energy. I'm going to go down 10I1. And back to my starting point, so that all my delta V should add up to 0. Okay, there are the 3 equations we're going to use to solve this problem. If I do a little quick take a look, the only change we said in the circuit was flipping the direction of this. And so when I look at my 3 equations, you say that's the same, that, right, is the same. This one, the only thing different is the sign there on that. But that is going to yield a different answer for us. So going through doing some math now. Now I'm just going to do the math on this, and figure this out. Once again, I've got an equation that only has I2 in it, so I can solve the value for I2 very quickly. One that only has I1, so I can solve for I1 real quickly. Once I have I2 and I1, I can plug them back in here and solve for the total thing. So here we go, doing the math real quickly. Okay, so taking a look at this, you say, let's just make sure that this makes sense, what's going on. We notice that we got positive, negative, positive in our currents, which means the direction was just incorrect for I1. I1 needs to be flipped, so that's going this way. So what's going on in this circuit really is that I have my current going this way, right? And then my current going this way, right? Yeah, so what's going to happen here is I've got current going... Yeah, right. Yeah. Okay. So the great big 12-volt battery pushes current this way, right? The 6-volt wants to continue pushing it that way, right? But it's going to like push it around like this. So current's going to be going around the outside like this. And in that middle branch, it's getting pushed again. This ended up being the correct sign this time, right? So actually, that battery is actually pushing up. So what's happening is the current's coming out, right? And it's going up and around like this, right? Which is the way you would expect it. It's not going backwards through any of the batteries this time, right? So now we're going to take a look at Kirchhoff's loop law problem number 3, all right, or Kirchhoff's law problem number 3. And so we're going to set up a junction law and 2 loop laws for the circuit. This time, notice that they did something a little bit different. And this time, they told us one of the currents. And you say, oh, well, that means now there's only going to be 2 unknowns. Oh, but wait, they didn't tell you the delta V for this battery. Okay, so actually, it's still going to be 3 unknowns, 2 unknown currents and 1 unknown voltage. Okay, they could also have done a problem with an unknown resistance if they want to make one of the resistors unknown. There's different ways of setting it up, and you can solve them with the same technique. So, starting off with our junction law, I'm going to go ahead and, what the heck, we'll kind of keep with how we've been doing it. We'll do the junction law for the bottom junction. And we'll say, hey, all the currents going in equals all the currents going out. You say, hey, what's going in towards this junction? Well, I2 is going in, I1's going away, and this 3 amp is going away. So currents in equals currents out. My current in, I2, has to equal currents going out, I1 plus 3. Okay, the 2 currents that are going out of the junction. Now we're going to do loop laws. Again, we can do the outside loop, the left loop, or the right loop. I'm going to do the left and the right loops. The left loop, I'm going to choose to start at the low V side of my biggest battery, and I'm going to choose to read the circuit going around through that battery, which means I'm going to end up going, actually, it turns out, clockwise in this case. So first, we're doing our loop laws. I'm going to do the left loop. And so first I'm going to go up 9 volts, going from the low V to the high V side of the battery. Now I've got 3 amps going through 3 ohms, right? And I'm going with the current. So from before we lost the energy to after, so we're going to go down I times R, down 3 times 3. And now I'm going to go with the current through this. So this is going to go down 6I2. Now I'm back to my starting point, so that should add to 0. Let's do the right circuit, the right loop, I should say. Again, I'm going to start the low V side of my biggest battery. To the left here, this big V guy, and going to go go around clockwise on this side. So first I'm going to go up. So we're doing the right loop. I'm going to go up V. Now we're going to go, look, I'm going against the current. So the charges flow with the current through and they dump energy off here, and then now they've got less energy per charge. We're at a lower potential here. So we're going to go from low V to high V. We're going to go up IR. So we're going to go up I1 times 4, up 4 I1. Okay. Now we're going to go against the current here. So from after the lost energy to before the lost energy, we're going to go up IR. So we're going to go up 6 times I2. And now we're back to our starting point. So all those changes in V should add up to 0 because we're back to the starting point. And there was my 3 equations that I'm going to use to solve. Okay. I notice that this equation has 3 unknowns, V, I1, I2. This has 2 unknowns. This one only has 1 unknown. Holy cow, that's going to be quick and easy to solve. Let's go ahead and use this to solve for I2 right away. 9 minus 9, you say, wait a minute, 9 minus 9, that gives you 0. Minus 6I2 is 0. You're like, what? You get I2 equals 0? You're like, what's going on there? That's really weird. Okay, there is something very important happening in this circuit. I'm going to come back and talk about it in just a minute. Let me go ahead and finish up the problem and solve for the rest, and then we'll talk about what happened and why. Now we know I2 is 0. It's pretty easy to take this equation now and say, oh, I2 is 0. Substitute an 0 in there. 0 is I1 plus 3. I can see that I1 is going to be negative 3 amps. Now that I know my values for I1 and I2, then in this green equation, knowing the values for I1 and I2 is going to let me solve for V. So if I do that, I'm going to have V plus 4 times negative 3, right? Because I1 is negative 3 amps. And then plus 6 times 0 equals 0. And so I can see that V is going to be 12 volts. Okay. Yeah. And there's my solutions. So what's going on here? Why are we getting 0 for our current in that middle branch? Well, here's what this is saying. Look, I1 is flipped backwards. I1's actually going this way. So you say, what's happening now is this big 9-volt battery and this big 12-volt battery. 9-volt battery pushes the current around. 3 amps go around, right? They come through here. And then somehow none of it goes this way. It all just keeps going. This battery pushes it to, this 12-volt battery pushes it to. And my current is just running around the outside. And there is nothing flowing through this 6-ohm resistor. Okay, like, well, how is that happening? Well, we're going ahead and we're going to push. Now, let's just say that this is kind of like my starting V value. If you want to say, let's just arbitrarily say that this is V equals 0 right there. My current, we go up 9 volts. Now I have 3 amps through 3. We go down 9 volts. Look, that means the V value here and the V value here are the same. The voltage is like, I don't know what you want to say, balanced. It's the same V on both sides. That means to get from here to here, if I did a little path, right, you'd say I'd have no delta V from here to here. And that means there is no E field pushing from there to there. There's nothing to shove the electrons through that resistor. The V just happens to be balanced. There's no delta V. There's nothing to push the charges through. If I go around this way, now I go up 12 volts, right? But then I've got this, what does this current here end up being? I1 ended up being 3 amps. So I've got 3 amps through 4 ohms. I go down 12 volts. So I go up 12 volts to this battery. I go back down 12. So the V here and the V here are the same again. And so there is no reason for charge to go through this. Nothing is going to flow through this resistor. There's no delta V to push charges through that resistor. I know that if charges were flowing through this, they would dump off energy in there. And so I'd have to have a change in V. There isn't none. There is no change in V, so it must have no current through. Weird, huh? Now, why do I point this out? It's kind of a weird freak special case. They happen to perfectly balance. We design devices that will work like this. We call circuits like this are kind of like bridge circuits, where I'll have some path here, and maybe on one side I'll have an adjustable resistor, or I can do things with adjustable capacitors too, but adjustable resistor. And maybe over here there'll be something that I'm like trying to find the resistance of. And so I can adjust the resistance here, right, to change the amount of current flowing, the voltage, and everything, so that the current going through here goes to 0. And like I'll design a circuit. So this is not a good example, but basically I'll have like an ammeter here, maybe, right, measuring the current that's flowing through this. And when I adjust it to the point, when I adjust the adjustable resistance that like kind of balances out the resistance on this side of the circuit to this side, sort of thing, when it balances out, makes it so that there's no current flowing through or whatever, the voltages balance out across here, then I know I get no current through that ammeter, and I'm like, aha, I know that this value, now I know it's got to be the same as this value, sort of thing. Viren has a video specifically about bridge circuits, and that's something you'll want to take a look at. Bridge sort of circuit, because it's something that we use in actually in designing different meters and stuff. It's something that they want you to know about, and they come up on the AP exam fairly regularly. There'll be a problem with like a sort of a bridge circuit where there's a part where like we're going to try to make the voltage balance or whatever. So that is something to take a look at. Kirchhoff's law problem 4. Circuit problem 4 looks an awful lot like circuit problem 3. You say, what's the difference? You say, look, 3 ohm resistor, 6 ohm resistor, 4 ohm resistor, 9 volt battery, right? The difference is in problem 3, they told us this current and made us solve for this voltage of this battery, which ended up being 12 volts. In this circuit, they don't give us this current, but they do give us a voltage of the battery, but it's only 8 volts. Okay, and another difference. This, in problem 3, the battery had the low V side on the left and the high V side on the right, so it was going to try to push current that way. Now it's set up the other way, flipped the other way around. It's going to try to push current that way. So in this problem, the voltage is balanced out just right. So the delta V across this middle branch was 0 and there was no current through. We're not expecting it to balance out this time. Let's go ahead and set up our equations. We're going to go ahead and start off with the junction law. I'm going to apply that to the bottom junction. Currents in equals currents out. What's going in towards that junction? Just I2. Currents going away, I've got I1 going away and I3 going away. So I2 equals I1 plus I3. Into the junction equals out of the junction. Now we do some loop laws. Let's go ahead and start with that left loop. I like to start reading the circuit a little bit on the low V side of the biggest battery. So I'm going to start here. I'm going to go around, in this case, clockwise. Right. So first I'm going to go up 9 volts. Then I'm going to go down. I'm going with the current. So from before they lost the charge to after. So we're going to go down IR. So we're going to go down 3I3. Now I'm going with I2 through that center branch. So we're going to go down 6I2. And it takes me back to where I started. So the total change in potential better be 0 if I'm back to my starting point. Now we're going to go ahead and do the right loop. Again, I'm going to start at the low V side of my biggest battery. I'm going to go through that battery. So I'm going to go up 8 volts at the start here. I'm doing this loop around counterclockwise. And so I say, so first I'm going up 8 volts. Then I'm going to go with the current with I2 through 6 ohms. I'm going to go down 6I2. Now I'm going with I1 through the 4 ohm resistor. So I'm going to go down 4I1. And that takes me back to my starting point, so the change in V better be 0. There are my 3 equations I'm going to use to solve this circuit. This set of simultaneous equations, you say, take a look. This one has 1, 2, 3 unknowns. This one has just 2 unknowns. This has just 2 unknowns. All of them have multiple unknowns, so I can't just really quickly solve for one. I'm going to have to substitute through and work through the system. I'm going to start by... it's kind of arbitrary where you want to start at this point. I'm going to choose let's eliminate I3, and then let's eliminate I2. And so with this one, I can rewrite I3 in terms of I2. So that's what I'm going to do. And then with this one, I can rewrite I2 in terms of I1. And then I'll have an equation for I2 in terms of 1. I can use that expression. Yeah, you'll see what I do. Okay, so now I have I3 in terms of I2 and I2 in terms of I1. Well, if I know I2 in terms of I1, I could put this in where it says I2, and now I have an equation for I3 in terms of I1. So I'll have I3 in terms of I1 and I2 in terms of I1, and I can just put those in here and just have an equation with just I1. So let me go ahead and substitute into this guy. I'm going to take this bit. So now I can take this and substitute it in where it says I3. I can take this and substitute it in where it says I2, and I'll have an expression just with one variable, just I1. So now I can tidy this up. It just comes out nicely to be 1/3 of an amp. All right. Now I know my value for I1. I could now here's I2 in terms of I1, so I can just find I2, and here's I3 in terms of I1, so I can find I3. So putting that 1/3 amp in there is 10/9 of an amp. Okay, going to do the same trick over here. Is 7/9 of an amp. Okay, so there's my three answers. I can double check that this makes sense. Notice that all of them came out to be positive. That means the directions are actually correct on the original diagram. The current flows down and then comes around like this. And that makes sense. Look, the big 9-volt pushing the current this way, the big 8-volt pushing current this way. So they're just going to push it around and around and around like this. And so at this junction, what's happening, look, I've got coming into the junction, I have I2, that's 10/9. And what comes out? Well, what goes this way? 1/3, that's 3/9. And what goes this way? 7/9. 3/9 and 7/9 is 10/9. It makes sense. And so that's problem 4. So we're taking a look at circuit problem 5, or I should say Kirchhoff's law problem 5. Let's take a look. First thing I notice is you're like, wait a minute, it looks like there's 4 things to solve for here. You're like, well, wait a minute. This is like those other circuits just turned sideways. Aren't we just going to get 3 equations and 4 unknowns? What's going to happen? This is actually just taking a voltage reading across this resistor. Okay, so if I cover that up, this is actually, we have all the resistors, we have all the batteries, and we just have 3 currents to solve for. We can get our 3 equations, 3 unknowns, solve for all these currents. Then I can just use Ohm's law to do delta V as IR here. So it's nothing to worry about. It's all good. Okay, so let's start up. Let's go ahead and get our junction law. I'm going to choose to use this left junction. Notice they've got the 3 currents labeled for you. And you say, now, wait a minute. All these currents are going away from the junction. So if I do sum of the currents in equals sum of the currents out, I would have 0 going in equals I1 plus I2 plus I3 exiting, going away, going out of that junction. That's all right. That means that at least one of these is labeled incorrectly for direction. It's all good. At the end, any that are going the wrong direction will just come out to be negative currents, and we'll know, oh, it'll be the right magnitude, it'll just be the wrong sign. And so we'll know, oh, just flip it and everything's good. So no big deal. Now let's go ahead and do our loop laws. Again, I could do loops outside. I can do the upper loop. I can do lower loop. The upper loop I could do clockwise or counterclockwise. I would get equations that would be the same, just if I go, instead of clockwise, I go counterclock, it'll just flip the signs on all the terms. It's as if I just multiplied everything by -1. That doesn't change the equation. So either way is fine. We're just going to go ahead and do top loop and the bottom loop. Okay, I'm going to choose to do for my 2 loop equations. Okay, so let's go ahead and do the top loop. I'm going to go ahead and start the low V side of the biggest battery. I'm going to go through that battery. So I'm going to do this one, it turns out, clockwise. And so first I'm going to go up. Here's my loop law for the top loop. Okay, so first I'm going to go up 6 volts through that battery. Then I'm going to go backwards through this battery. I'm going to go from the high V to the low V side. So I'm going to go down 3 volts. Now I'm going to go against the current here. So I'm going to go from after the charges went through and lost the energy to before they went through and lost the energy. So I'm going to go up potential. So I'm going to go up IR. So I'm going to go up 20 I times I2. Now I'm going to go with I1 through the 8 ohm resistors. So I'm going to go down minus IR. So I'm going to go minus 8 I1. Now I'm going with I1 through the 12 ohm resistor, so minus 12 I1. That gets me back to where I started. So all my changes in potential had better add up to 0. I could go ahead, I could tidy this up a little bit. 6 minus 3 is just 3 plus 20i2. And look, minus 8i1 minus 12i1. Let's just make that minus 20i1. There, it's a little bit tidier. Okay, now let's go ahead and do the bottom loop. Bottom loop, I'm going to start the low V side of my biggest battery. I'm going to choose to go through that battery, so I'm going to go, in this case, I'm choosing to trace the circuit counterclockwise. Again, I'm not saying that's necessarily the way it's flowing, although it is. But it's just a direction I just arbitrarily chose to go. So here we go. So doing the bottom loop. So you say first, I'm going to go up 8 volts. Now I'm going backwards to that one, so I'm going to go down 3 volts. Now I'm going against the current through that resistor, so I'm going to go up IR. So I'm going to go up 20I2. Okay. Now I'm going to go with I3 through the 6 ohm resistor, so I'm going to go down IR, so down 6I3. Now I'm going to go with the I3 through the 9 ohm, so I'm going to go down 9I3. This gets me back to my starting point, so my delta V is 0. Again, I can go ahead, I can collapse this down, simplify a little bit. 8 minus 3 would be 5 plus 20 I2. And then see minus 6 and minus 9, that'll be minus 15 I3 equals 0. That's a little tidier. So here we go, 1, 2, 3. Those are my 3 equations I'm going to use to solve. I notice that I have 1, 2, 3 variables in this equation. Here I have just I2 and I1. Here I have I2 and I3. Let's rewrite I2 in terms of I1. So I2 equals something in terms of I1. And then here I can get, using those together, I can get I3 in terms of I1. Once I have an expression for I2 in terms of I1 and I3 in terms of I1, I can plug them in here and get one expression, just one unknown, I1. And I can solve for that current and then get the rest. So there's I3 in terms of I2. But what I want is everything in terms of I1. So I'm going to use this expression for I2, and I'm going to substitute it there. So here I have an expression for I3 in terms of I1. Here I have an expression for I2 in terms of I1. I could put both of these in here where it says I3 and I2, and I'll have an expression just with one unknown with I1. And so that is the plan. And so now I've got an equation with just one unknown. So it'll be 1/200th. So I1 is 1/200th of an amp. Now that I have I1, look, I can put that value in for I1 and get a number for I2. I can put that number for I1, put it in here, get a number for I3. So that's it. And so if you wanted to double check and make sure this makes sense, you say, this one came out to be negative, right? Which means that I2 is actually flowing the other way. So when I look at this circuit, I2 is actually going this way. Currents are coming out like this, coming in like this, out like this, together like this, splitting, coming together. And you say, look, it makes sense. Look, the big 6-volt battery and the big 8-volt battery are shoving charge this way and pushing it backwards through that 3-volt. Maybe perhaps this would be the setup if you're like recharging that battery, maybe, right? Maybe pushing it to charge backwards through it. That's the setup. That makes sense, which means these two had better add up. This is better work, right? So you say, hey, I1 and I3 that are pushing in this way better add up to be balanced out I2. I1 and I3, I1 is 1/200th. I3, you know what 7/50ths is in 200ths? That would be 28 200ths, right? Times 4 times 4. 28 200ths plus 1 200ths is 29 200ths. Oh, look, minus 29 200ths. That balances out to 0. Perfect. And that is circuit problem 5. Oh, wait, one last thing. Hey, now that we know all these values, and we could plug them all in. We're going to fill out the silly blanks. We want to know the voltage reading for this voltmeter. So we hook this voltmeter up, and we connect our voltmeter here, and here. What's the delta V? So I now know the current. I know how big I3 is. I3 is 750th amps. And I know the resistance there is 9. I can just do a delta V as IR. So I'm going to do a delta V is I times R. And so I'm going to say, hey, that delta V that we're trying to solve for, that's going to be my 750ths of an amp times the resistance of 9 ohms. And you say, that's going to be 63 50ths of a volt. Okay? And that's it. That's that problem.